I'll be presenting EyeNerf, a hybrid representation for photorealistic synthesis, animation, and relighting of human eyes. My name is Gengyan Li. I'm from the ETH Zurich and Google Research, and these are my fellow authors and colleagues. So let's start off with why. Why do we care so much about rendering eyes accurately? Well, despite taking up only a small portion of space relative to the rest of the face, rendering human eyes is actually extremely critical for the purpose of making people look alive. For example, a common saying is that a fake smile does not reach the eyes. As such, for purposes like VR teleconferencing, digital 3D avatars, multimedia productions, and other similar VFX cases, getting eyes right is absolutely essential when trying to create believable videos of the human face. In our work, we propose three main contributions. First, a hybrid model that is exceptionally well suited for the eyeball and cornea in particular. We also propose a novel method for regazing through the use of interpolation, and we propose a highly efficient, smoothly relightable extension to neuroradiance fields that works even for dynamic scenes, and all exceptionally high levels of quality and high resolution. Before we get into detail about our contributions, however, let's first look at how this can be done in current state of the art. One approach are traditional capture reconstruction techniques. In those methods, one would capture data of the human eye, such as through photos or videos, and then individually reconstruct every given component, typically using meshes, which can then be re-rendered under arbitrary conditions in arbitrary poses. However, most such methods do not model the periocular region, which would need to be reconstructed using some additional method. Doing so, however, would result in the additional problem of having to stitch together multiple methods, as well as jointly rig it such that the periocular region moves coherently. For example, the motion of the eyelid is very strongly correlated with the eyeball motion, which would also need to be accounted for if separate motion models are used for the face region and the eyeballs themselves. So what makes the eye region so hard to model in the first place that it requires its own specialized method? Well, first off, the eyeball itself is actually already quite complex in terms of light transport. The cornea, the part of the eye that bulges out from the iris and bends the light, exhibits extremely specular reflection. As we can see here, the individual spotlights in the scene are clearly visible on the reflection of the cornea. Furthermore, the cornea also exhibits strong refraction, which bends light rays and camera rays onto the iris, as can be seen quite clearly from side views such as here. Both of these effects, both reflection and refraction, are of extremely high frequency as well. In addition to that, there's also the issue of subsurface scattering. Although this mostly occurs on the skin, it exists to some degree on the eye white or sclera as well. Furthermore, the sclera is both bumpy and highly specular as well, as we can see here. And that's just the eyeball itself. Both the eyelashes and eyelids are relatively fine structures that are difficult to represent accurately using traditional meshes, especially when motion needs to be taken into account, which is usually highly correlated through the eyeball and eye region. Before we go further, however, let's first look at what NERF is. NERF, or neuroradiance fields, are a recent representation initially proposed by Mildenhall et al., which approximate scenes using a view-dependent radiance volume. NERFIs, by Park et al., extends NERF to additionally model dynamic scenes by learning a deformation field for every frame between the observed space and a canonical volume. One significant problem with modeling the eye using NERF or NERF-like methods is rendering the cornea. As we previously mentioned, the cornea exhibits extremely specular reflection but also strong refraction. The former is difficult to model as NERF tends to have issues with very high frequency view-dependent effects, while the latter suffers from the fact that refraction is not supported by standard NERF. As we can see in this video rendered using NERFIs, which we've modeled to work using with data including multiple lighting conditions, it can still model the cornea to some degree by using view-dependent effects to make it look similar to refraction. However, doing so requires effectively hallucinating something that isn't geometrically correct, resulting in overall very poor quality, especially from side views, as we can see here. On the upper left, we show a virtual mirror ball, which shows the desired illumination condition. We clearly see that the shape and quantity of lights do not match with the reflection on the cornea. This motivates our first main contribution, our hybrid model, which uses both an explicit eyeball surface and implicit nerf volume. The nerf volume, despite being defined by an underlying neural network, is still ultimately a volume, and can be treated as such from a computer graphics perspective. Therefore, we can insert a refractive surface into the volume and otherwise render it in a very similar way. Any camera ray that hits the surface is treated identically until it actually hits the surface. Then we can split the ray into a refracted and reflected ray, with the directions being computed using the standard physical laws governing material transitions. Although the ray has been bent and split, we can still query the neural network at the new sample locations without a problem, as the network is ultimately agnostic to where the points came from. Again, we re-emphasize that despite NERF being a neural network-based approach, ultimately it can still be rendered and manipulated using many traditional volumetric rendering techniques, as we do here. The surface shape and pose can then be learned using differentiable rendering, as the bending and reflection can be formulated in a fully differentiable manner. This addresses the issue of a static cornea, but we don't want a model that can only represent a single static frame. We want a dynamic, controllable one that can look in any desired direction. First, the periocular region can be handled using a deformation field, akin to NERFIs. This allows for dynamic motion of the eyelids and skin. Our explicit mind model can also be extended to work in dynamic settings as well. Though the shape remains globally consistent, we now learn a per frame pose instead of a single one. This also allows us to use the rigid transformation of the eyeball surface model to warp the eye volume, instead of using a deformation field, which reduces the amount of information that needs to be contained in the deformation field itself, and also provides stronger consistency guarantees for the volume inside the eyeball. Using just what we've mentioned so far, we can now already produce high-quality novel view synthesis of any captured frames. We show an example here. On the left, we show results using our hybrid model, and on the right, without the explicit surface. Already, we show a noticeable improvement in terms of quality compared to using just NERFIs, especially comparing the area near the iris. Not only are the specular highlights much clearer and match the shape of the lights, but the overall iris shape is much clearer as well. Here are some more results on other subjects. Next up, let's look at how we perform regazing. To perform regazing, we note that we have two main components in our model, the periocular region and the eyeball. In order to regaze the eyeball, we can rigidly manipulate it and precisely control where it's looking at by changing its rotation. In order to produce plausible regazing, however, we also need to deform the periocular region to ensure the overall motion makes sense, rather than just moving the eyeball around alone. To do that, we select a few training frames from which the subject is looking at directions around the targeted gaze direction and interpolate between the deformation field of those three frames. The highly correlated nature of the eyelid motion already makes this look quite realistic. For example, when we combine the two, we get the following appearance. Note how the eyelids and immediate periocular region quite plausibly and realistically follow the eyeball motion. Finally, we add relighting capabilities. Relighting in the context of neural radiance fields is a rather difficult task. More specifically, computing the full light transport equation in a volume naively would require recursively tracing secondary arrays for occlusion and indirect lighting, and be computationally intractable if we take into consideration the relative slowness of NERF evaluations. NERF, or Neural Reflectance and Visibility fields, address this issue by approximating multiple components of the full light transport equation, in particular occlusion, that's just evaluated in a neural network once. However, NERV still produces relatively noisy results. The shape of shadows is quite decent actually, but the texture acquires a very noticeable noise pattern. Furthermore, their method cannot handle dynamic scenes. For our method, we note that although approximating the occlusion is a good first step, the majority of the physically based light transport equation, in fact, can be factored away. Instead of modeling occlusion, indirect lighting, and reflectance separately, we can instead treat them as one single black box equation. After all, that's the actual signal that we have. We know how much light goes into the scene and how much comes out. The actual light transport is in some sense a black box. We don't directly measure how it's transported, and for the purposes of rendering an image, it isn't necessary either. This leads to our second main contribution, our spherical harmonics-based lighting method for NERF and NERF-like methods, which we denote as NERF SHL or NERF with spherical harmonics lighting. I'll explain a bit more about the spherical harmonics part in a bit, but let's look at how it works a bit more generally first. Our network needs to take in as an input the light direction, the world space point, and the view direction as inputs. And as an output, it needs to produce the opacity, as well as the total amount of light transported, as a factor of the colored light intensity. However, this would require evaluating our network once for every single light source in the scene, which would make it quite expensive to evaluate and train on if there are multiple. We therefore move the light direction into the output space of our network, effectively predicting an entire function instead. To do that, we formulate our network output as spherical harmonics coefficients, which then describes the light transport function with respect the light transport factor as a function with respect to the light direction. We then additionally split our light transport function into a view-dependent specular light transport function and view-independent diffuse albedo and diffuse light transport function. Again, both functions in the form of SH coefficients. These light transport functions can then be integrated with a full environment map to compute shading values. Then the diffuse shading is multiplied with albedo and added to the white specular shading to compute the final RGB shading values. Doing a full integration with arbitrarily complex and high-resolution environment maps, however, would still be extremely expensive if we had to do it for each sample point. However, due to the properties of the spherical harmonics functions, we can actually reformulate the integration to be independent of the actual function coefficients. The full derivation can be found in our paper, but ultimately the integral can be reduced to a dot product of the predicted SH coefficients with corresponding pre-integrated values that only need to be computed once per environment map, resulting in our network being almost as efficient as the original NERF network, requiring only a few more products and sums. As we can see in this example, we note that our method can still fully model excellent, relatively hard shadows quite plausibly as well. Furthermore, due to the smoothness of spherical harmonics, any error that shows up is more likely to show up as blurring rather than the noise that we see in NERV, which is arguably far less visually distracting. We then add the previously mentioned warp field and rigid transformation to support dynamic scenes as well. Finally, in order to support correct shadowing in a dynamically moving scene, we additionally directly condition our network on the world space points. As we do not use scenes with strongly shifting shadows, this serves as a sufficient approximation. Although the eyeball rotates in and out of the shadow as it moves, the location of the shadows themselves remains mostly consistent in world space. Next, let's take a brief look at the capture setup we use to obtain training data. We use 4 off-the-shelf high-quality static cameras and 8 off-the-shelf multi-spot light boxes attached to a fixed frame. We also use a handheld high-intensity light in order to get diverse lighting conditions. Using just 4 views, however, is usually insufficient to train a high-quality NERF model. In order to get more views, we attach marker tags to the subject's face and recenter the world space coordinate system based on the tags. By taking advantage of relativity, we can then have the subject rotate their head, effectively rotating the entire universe, which includes the cameras, around the tags, which produces the dense number of views necessary to train a NERF well. Finally, we show some more results of our method. As previously mentioned, our full pipeline can be used for simultaneous relighting, regazing, and novel view synthesis, which has not been accomplished by any other method so far in the context of NERF. Our SH formulation additionally allows us to decompose decompose any rendered image into specular shading, diffuse shading, albedo, and geometry. We can also relight using full environment maps, such as using the Grace Cathedral or the Ennis environment map, as we can see in these videos here. Note how the entire Grace Cathedral and Ennis door thing are reflected off the corneas of the subjects. Finally, we can even use a full dynamic sequence, such as is in this scene here, where the subject is animated looking at downwards falling letters. In summary, we proposed a novel rendering method using NERF, which includes a novel hybrid model which is especially suited for rendering human eyes. We proposed a regazing method using interpolation, and we also propose a highly efficient relighting method that works even for scenes which are deforming. Thank you for our attention, and we invite you to read our paper or come to our Q&A session if you're interested.